In a campus network of almost any size, it is more than likely that we are going to encounter IP address and other optional assignments using Dynamic Host Configuration Protocol, or DHCP. In this module, we are going to talk about iOS DHCP fundamentals, and here we are going to first cover basic DHCP operation, how the clients and servers communicate with each other, and then we are going to see how the DHCP client, server, and DHCP relay are configured in Cisco iOS. DHCP is a client-server architecture. And in any network, we can have multiple DHCP clients. And keep in mind that these hosts, because they are using DHCP, they are very unlikely that they have any IP addresses configured. This is the job of DHCP, to assign IP addresses to hosts, among other things. And we can also have multiple servers in our network. So the basic operation of DHCP consists of exchanging different kinds of DHCP messages, and this is the client-server communication that we are going to explore. Also, in these messages, any number of DHCP options may be present. DHCP options usually have numbers like 50, 51, 49, 82, whatever they might be, and these are the options that carry requests and information about, for example, client host names, the client domains, the DNS servers to use, the TFTP servers to use, the location information where the request in the network is coming from, and so on and so on. We are going to talk about only a subset of these messages and subset of these options, and in some of the other modules we are going to dive much deeper into this, because this is not very straightforward sometimes. The basic DHCP messages that we are almost always going to observe in our network are going to be DHCP discover, DHCP offer, DHCP request, and DHCP acknowledgement. Let me show you how they work. So let's say that we have in our network a multi-layer switch, our Cat1 for example, that is connected to a host. And this host is requesting an IP address. So our Cat1 here is the server, and our host here is the client. The first thing that is going to happen is the host is going to send out a discover message. So this is going to be our DHCP discover message. Because the host at this point in time does not have an IP address, the source IP address in this request is going to be an empty field. It is going to be 0000. Now keep in mind, this is an illegal IP address, but this traffic, this packet, is not going to leave the local segment. It's going to remain on the same segment as our DHCP server is. At least that's the idea. But the source MAC address for this traffic is going to be the host's MAC address. The destination IP address of this traffic is going to be the broadcast address, which is 255.255.255.255. The destination MAC address for this traffic is going to be broadcast, or all ones, or all Fs. So let me just write this down so that you can actually see it. This DHCP discovery message is going to go out, as I said, on the local segment. If we have multiple servers, this message may end up being received by multiple servers, but we are going to keep things simple. Let's say that Cat1 is the only server in this case. So if this is the case, our Cat1 will need to respond to this request. Let me just delete this very quickly here. Very good. And our Cat1 in this case is going to respond to this sent discovery message. It is going to respond back with a DHCP offer. This DHCP offer is going to have a tentative IP address that host could use if the host decides to use this IP address. But much more interesting thing is that there could be some other things in that packet. There could be other options, like, for example, use this domain name, use these servers as DNS servers. If this was a phone, we could assign the call manager address, we could assign the TFTP address, and so on and so on. So we could do many other things in this DHCP offer. But even more interesting is, what is going to be the source IP address of this traffic? What is going to be the destination IP address? And what about source and destination MAC addresses in this case? Well, for source MAC address, that is very simple. Or let's say for the source IP address, let's use the same order here. So the source IP address is, of course, going to be the server's IP. Because remember, the server actually does have an IP address. The source MAC address for this traffic is going to be, of course, server's MAC address. And at this point here, I am in a little bit of a disagreement with official Cisco's information about what is going to be the destination IP address. That actually depends on the implementation of the DHCP server. Some DHCP servers are going to send this DHCP offer to a broadcast IP address, 255.255.255.255, just like the host did, but some DHCP servers are actually going to include the IP address, the destination IP address, to be that tentative IP address that they are actually offering to the host. It's still going to get where it needs to go, don't worry about that, but here I'm going to say that the destination IP address can be either broadcast, or it could be tentative offered IP. The destination MAC address, on the other hand, is going to be client's MAC address. So even though we are using the IP address that host is not using, we are still sending this to the MAC address of the host so that it actually arrives where it needs to arrive. But as usual, things are not that simple, always. In some cases, just like in the previous case with an IP address, sometimes this is going to be sent to the broadcast destination as well. And I'm going to show you that in a moment. So for now, just keep this in mind that this could be the client's MAC address or could be the broadcast address. Once the host has received an offer message from the server, the host is going to determine whether this is the address that it wants to use, and it's going to respond back. So we are going to answer our offer with the DHCP request. So now our host here is going to send DHCP request message, in which it's basically going to repeat the request, but this time including the IP address it wants to receive. Just like in the previous example, the source IP address of this traffic is going to be 000, because this IP address that we have been offered is still not in use by the client. The MAC address that we are going to be using is going to be host's MAC address. The destination IP address could be, in this case, either broadcast, or, because at this point in time the host actually knows who the server is, or it could be server's IP address, and destination MAC address is going to be either broadcast or server's MAC address. And last but not the least, there is going to be an acknowledgement. This is sent from the server, so this is going to be our DHCP ACK. The source IP is the server's IP address. Source MAC is going to be server's MAC. Destination IP could be either tentative IP or broadcast. And the destination MAC address can be either host's MAC or broadcast. Enough theory. Let's see this in action. To see this in action, I'm going to set up, again, a very simple setup network, or test network, I should say. I'm going to be using two switches, Cat1 and Cat2. And off Cat1, I'm going to connect my Wireshark listening station because I want to observe all these packets that I was talking about. And this is going to be connected on Fast Ethernet 03 of Cat1. Cat1 and Cat2 are going to be interconnected on port 24. And I'm going to make this a trunk. And I'm going to create two VLANs, 100 and VLAN 200, on both Cat1 and Cat2. I'm then going to create two SVIs on Cat1 and only VLAN 100 SVI on Cat2. And I'm going to configure Cat2 to be our DHCP client. I will configure Cat1 to be DHCP server in VLANs 100 and in VLAN 200. So this is 1 and this is 2. Off Cat2, I'm going to connect my Linux host in port Fast Ethernet 03, which is going to be an access port in VLAN 200, and this is going to be my DHCP client in VLAN 200. And Cat2 is just going to be acting as a layer 2 switch here. So it is going to act as a DHCP client in VLAN 100, but in VLAN 200 we are just going to pass the traffic from the Linux host and attempt to assign an IP address from Cat1. There is a reason why I want to show you different behavior between what Cisco is going to do as DHCP client here in VLAN 100 and what, for example, a Linux host is going to do. Let's start by setting up the basics. I'm just going to configure my VLANs, my trunks, and I'm going to configure SVI interfaces on my Cat1. So going to Cat1, I'm going to first create two VLANs. So I'm going to create VLAN 100 and 200. I'm going to create VLAN 100. I'm going to say IP address 192.168.100.1. And let's create interface VLAN 200. And I'm just going to give it a similar IP address with the third octet being 200. The next thing I'm going to do is I'm going to enable IP routing on this interface, or on this device. Then I'm going to go to interface Fastnet 24, and here I'm going to say switch port trunk encapsulation.1q. I can use ISL, but I prefer .1q. Switch port mode trunk, and switch port trunk allowed VLANs 100, 200. I don't really need to do the last bit, but why not? And let's do no shutdown here. So this is the configuration on Cat1. On Cat2, let's do similar thing. I'm going to configure or create two of my VLANs, VLAN 100, 200. I'm going to say interface. Oh, actually, I'm not going to create my SVI just yet. I'm going to go to interface Fastnet 24. I'm going to say switch port trunk encapsulation.1q, switch port mode trunk. and switch port trunk allowed VLAN 100, 200, and let's do no shutdown here. So I should be seeing my Fastnet 24 coming up, and if I do show interface trunk, I should be seeing that the trunking mode is on, encapsulation is at .1q, it's trunking, native VLAN is 1. I don't care about the native VLAN at the moment, and I can see that VLANs allowed on the trunk are 100 and 200. Let's do the same thing on Cat1 here. So this is in place. Let's now set up our Wireshark monitoring here. So I forgot to mention that I will simply copy all the traffic from Fastnet 24 and send it down to the Wireshark so that I can examine what is going on. So I'm going to go to Cat1. I'm going to say monitor session 1 source interface Fastnet 24. I'm going to say monitor session 1 destination interface Fastnet 03 and encapsulation replicate because I want to keep all the VLAN tags that I had there. And interface Fastnet 03, I'm going to say no shutdown there. Going to my Wireshark station here, I'm going to make sure that I'm collecting the traffic from Ethernet 2 interface, which is connected to Cat1, and I'm going to capture only boot P packets. Now, when you're using Wireshark to capture DHCP packets, you need to type in the display filter that you want to see boot P. And I can start the capture right now. I'm not going to be seeing anything because I don't have any servers or DHCP clients configured. Let's now see what are the steps required to configure the DHCP server. It is actually very straightforward and very easy. The first thing that we have to do is globally enable DHCP functionality, and it is by default globally enabled, and we can do that with service DHCP in the global configuration mode on our device. The next thing is we have to create a DHCP pool or multiple pools. DHCP pools are basically configuration segments that tell Cisco IOS what parameters to assign to whom. We have, generally speaking, there are other kinds, but generally speaking, two types of DHCP pools. We can have a network pool or we can have a host pool. Network pool is the pool of addresses that is going to be used if we have more than one client that we want to treat equally. That means we don't care which exact IP address we assign to a particular client, but we want to assign a IP address from a certain network. These pools are called network pools, and here we can see an example configuration of the network pool. We simply say IP DHCP pool and give it a name. Let's call it my pool 1. We say network, then specify the network and the netmask /24. We can specify other parameters like, for example, the DNS name to use, the DNS server to use, the default gateway. We can use all sorts of things there, but by default this should be enough. Host pools, on the other hand, are pools that are going to be used to assign certain set of parameters, like for example an IP address, to a particular client that needs to be identified using some method. The most common method to identify the clients for this kind of specific IP address assignment or parameter assignment is to use the MAC address of the client. So here I have specified the MAC address of my Linux host, but those of you with sharp eyes are noticing that this is not exactly a very correct MAC address. It actually has 1 byte more. That 1 byte more is at the beginning of this client identifier, and in 99.9, well, let me say, in all cases, it is going to be 01. It's a media type, media identifier, and 01 simply identifies the Ethernet network type. And then the next thing that we are going to do there is, instead of using the network statement, we are going to say host and then specify a particular IP address to use. So in this case, I want to assign to my Linux host an IP address 192.168.200.200 with the mask /24. Let's go ahead and configure this. So the first thing that I'm going to do is I'm going to go to Cat1 and I'm going to globally enable the DHCP service. So service DHCP. I know it's enabled by default, but it never hurts to actually enable it. Then I'm going to create the pool. And remember, the pool settings are exactly this. I need to say IP DHCP pool, have to give it a name, and specify the network that I'm going to use. So let's do that. I'm going to say IP DHCP pool. I'm going to call it, in this case, let me not just copy paste whatever I had there in that slide. I'm just going to say that this is, for example, going to be used for VLAN 100. And I'm going to say network 192.168.100.0/24. And let's, for some reason, say that, let's say that the first half of this network, the first half of these addresses, are addresses that I want to use in static assignment. So I don't want to use them for DHCP addressing. I can accomplish that if in the global configuration mode, I say IP DHCP excluded address and then specify the range. So I want to exclude the addresses 192.168.100.0 to 192.168.100.127. So I want these addresses to be excluded from IP assignment scheme. So I want to assign only the second half of the addresses. This is enough for now. I'm going to go back to the host pool. Let's see how the DHCP client is going to be configured in Cisco iOS. If you thought that configuring DHCP server in iOS was easy, take a look at the client configuration, even simpler. All I have to do is globally enable the DHCP functionality, again with service DHCP, and then on an appropriate interface, all I have to say is IP address DHCP. And that's it. I could specify a specific client identifier unless I want to use whatever iOS is going to choose to use directly, but I'm going to, in this case, skip that, and I'm just going to configure it using the default settings. All I have to do on cat2 at this point is to go into the configuration mode, say service DHCP, then I'm going to go to interface VLAN 100 and I'm going to say IP address DHCP. If I press enter now, my DHCP transaction process is going to begin. But before I do that, I want to make sure that my Wireshark is actually capturing the traffic, and I can see it is capturing. So now I'm going to go ahead, press enter here, and go back to Wireshark to see all this stuff that I just talked about. And let me show you a couple of things here. The first thing that we can see here is that we had a DHCP discover message. It went out and we can see that the source of this message was 0000 and that the destination of this message here was broadcast. Then we can see that there was an offer message, so this was coming from our server, and it was again going to the broadcast address, just like you would see in Cisco documentation, for example, or Cisco press books. Then we have the DHCP request. It goes from 0 to 255.255.255.255, and finally we have the DHCP acknowledgement. Now let's examine these packets in a little bit more detail. So I'm going to first look at the DHCP discover, and the thing that I care about here, first of all, is going to be the part that deals with layer 2. I can see that the source address was the MAC address of our client, just like I said it would be, and we can see that the destination was actually the broadcast. Now, if I open the Bootstrap protocol field here, I'm going to see one interesting bit of information. And that is going to be this part here that says bootp flags. And I can see that this first bit is set to 1, which is a broadcast flag. Now, this instructs our server to respond using broadcasts. This is the reason why all the communication here from server to client was done using broadcasts. And I can see that these were actually broadcasts because if I go here, so this was the response from the server, I will see that the destination MAC address here was the broadcast MAC address. It wasn't the client's MAC address. Let's see what happens when I bring my Linux box into the mix. Obviously, the next step in our configuration would have to be to configure the pool for our Linux host. Now, I could copy this configuration that I have here displayed, but I would like to show you one more thing. Linux DHCP client by default is a little bit different than Cisco's DHCP client. It is not going to include one DHCP option in the initial discovery message, which is the actual client identifier. So Cisco's iOS DHCP server interprets this perfectly fine DHCP discover message as a bootp request. Now, if we configured our DHCP server in this way here, this client identifier formatted like this is going to be ignored in our host pool because Cisco doesn't think that the incoming request is actually DHCP request. It thinks it's a boot P request. Now, we can still assign this client a proper IP address, but we have to identify the host in our host pool with a slightly different method. So we are, instead of client identifier, then this client identifier that I explained is the combination of the MAC address and the actual media type for Ethernet, what we need to do is we just need to use the client's MAC address. So let me show you how that is done. I'm first going to go to Cat1 and I'm going to create a host pool. So I'm going to say IPDHCP pool and I'm going to call it V200, stands for VLAN 200. I'm going to say here hardware address. So instead of using client identifier, I'm going to be using just a MAC address of my Linux PC. And for convenience, I have copied it in my clipboard. And then here I'm simply going to say, instead of using network statement that I used before for my V100 pool, I'm going to use a host command, 192.168.200.200/24. So the resulting configuration on Cat1 now is, so let me show you the DHCP pools here. I have V100, which is a network pool, and I have V200, which is a host pool, where the host is identified based on the MAC address. The next thing that I'm going to do is I'm going to go to Cat2, and I'm going to make sure that my FastInternet03 interface is properly configured. So I'm going to say switch port mode access, actually interface FastInternet03, switch port mode access, switch port access VLAN 200, and spanning tree port fast. Now I am ready to start testing this, but before I do that, I want to make sure, number one, that my Wireshark is actually capturing traffic at the moment. It is capturing, I am not getting anything there. And the second thing is, I want to go to my Linux box and prepare it to bring the interface up. Now, this is obviously not a Linux networking course, so I'm not going to teach you how to configure Linux to be a DHCP client. I have made a simple script that I can use to trigger the generation of the DHCP request. So I'm just going to say that on my connection to switch 2, I want to use the DHCP address. The next thing that I'm going to do is I'm just going to say here on my Cat2, I'm going to say no shutdown, and I'm going to go to my Linux box and start the process. And let's see if this generated what I wanted to do. And here it is, the exact picture I wanted to show you. Now, take a look at the source and the destination of our DHCP Discover. It is what we expect it to be. The client is using all zeros as the address, and the destination is our broadcast address. However, the source and the destination of server's offer response is very different than it was before. Now we can see that server is actually using the tentative client's IP address as the destination IP address. And we can also see here, so let me switch to offer, that the server is actually sending this response directly to the client. It is not broadcasting it. We can see here that the actual request repeats the same pattern as we had in the discovery process. The client is not yet using the tentative address. The broadcast packet here is sent towards the server. We can see that it's also sent to the broadcast MAC address, but the response from the server here is again unicast this time. Now, the reason for this difference in behavior is that here in the original discovery message, where we had our boot P flags, remember that one bit that was set to 1 when iOS was the client? Well, here, in a case if you are using Linux in your network, it is going to be 0. And this is telling the server to actually use unicast responses. But the important thing is that the client actually got assigned the correct IP address. We can see here 192.168.200.200 as the assigned IP address. So this should cover the very basics of operation of DHCP. But let's take a look at some of the options that we can configure in the DHCP server and assign to our clients. One of the most commonly used DHCP options is to assign a default gateway to the client. So let's use our Cat1's network pool to assign Cat2 the default router. To do that, I'm going to go into my DHCP pool configuration. So I'm going to say IP DHCP pool v100, and I'm simply going to say default router, and I'm going to say that Cat1 192.168.100.1 is the default router. So if I go to Cat2, what is the easiest way to actually ask Cat2 to ask for a new address? Well, I could shut the interface down and do no shut, or I could say release DHCP and then specify the interface on which I want to release the DHCP assignment. So in this case, I want to release the information from VLAN 100. If I do show interface VLAN 100, what I'm going to see here is that internet address will be negotiated using DHCP. I could wait a little bit for this to happen, or I could do the impatient thing and actually shut the interface down and then wait a little bit and then do no shutdown, which is going to trigger Cat2 to actually request the IP address from the other side. Now, I wanted to show you release just because it is going to generate a packet that goes out to Cat1, and it actually is going to tell it, I am no longer going to be using this IP address. You can free it up for someone else. So now, at this moment, we have received our information from Cat1. Let's see if we have the default route. So if I do show IP route, what I should be seeing now is that the route, the default route has actually been installed. And I can see that it's going to show up in my show IP route as a static route, but take a look at the admin distance of it. The admin distance of it is going to be 254, which is just one short of being the worst possible route, the route that is not going to be used. And which brings me to another thing that I want to show you. What if you have a client that is receiving a default route from the server, but we don't want to use that default route? Well, the answer is right there in the admin distance. What we could do here is we could say no IP DHCP client, no IP DHCP dash client, and we can say default router, actually it is going to be IP DHCP client default router, and distance, and let's set it to 255. So now, if I do show IP route, I'm still going to see that route in place. So let's request a new one. So I'm going to go to interface VLAN 100. I'm going to say shutdown. So I want to get rid of all the DHCP information that I have at this moment. So if I do show IP route, I shouldn't really be seeing anything there. And if I do no shutdown, I'm going to resend the DHCP request. And let's see what happens with the default route now. So if I do show IP route now, I'm not going to see the default route installed in the routing table now because it has the untrusted admin distance. Default router is by far not the only option that you can specify in the pool. There are many others that you can specify. Some of them have their name, like for example, you can say that we want to use the domain name. So now, if you want to assign cisco.com, for example, to our client, but there are some options that don't actually have their predefined name in the iOS configuration. Then you have to specify by specifying the actual value of the option. So for example, for option 150, let's say that this is going to be an IP address, and we can say that whatever option 150 is, it is going to be an IP address 1111. So you can specify any options that you want. Some of them are reserved, some of them have a particular name that you can use in the iOS, and some of them you just have to code with their option number. Now, where can we see these option numbers? Well, let's go back to our Wireshark and let's take a look at that. So here is the copy of the last DHCP acknowledgement that we received. And here we can see that we have very many DHCP options that are actually in use. And one of them is this option 3 that says router here. So if you open this one here, we're going to see that this was the default gateway that was assigned. Let's re-request the IP address and let's see that domain name and option 150 that I've configured actually take effect. So I'm going to go to interface VLAN, actually on cat2, interface VLAN 100. I'm going to say shutdown here. And while I'm at it, let's go back to Wireshark and let's restart this capture so that we have all the negotiations from the beginning. And let's say no shutdown, and I'm going to go back to Wireshark and see what is happening here. So I can see here in the offer that I'm going to have options here, and options ended up being open. So let me close them down, see if they're all going to close down. Yes, they will. And here in the offer, I'm seeing that I had the domain name, which is option 15. You can see that I had cisco.com specified, and option 150, I was joking around when I said whatever it is actually the TFTP server. It's one of the options that you need to use if you are using Cisco IP phones, for example, to tell them what is going to be the TFTP server address. And here, if I open this option, I'm going to see that I told my client, if for whatever reason it wants to use the TFTP server, it should find it at the address 1111. I think this covers the basics of the DHCP server and client to some detail. The last item that I'm going to mention is going to be the configuration of the so-called DHCP relay. In many cases, the DHCP server is not going to be on the same network, on the same physical, on the same broadcast domain as the clients. It could be a centralized server. In this case, when we have this situation, the default gateways or the router's devices that are going to be acting as the default gateways on those segments where we have clients, they need to groom all the DHCP requests and actually send them to the remote server. Let me show you in the whiteboard what I actually mean by this. Let's say that we had a network where we had a switch that has relatively many clients connected here. And these clients may be in multiple VLANs. Now, this switch here is also acting as the default gateway. So we have layer 3 interfaces configured here the SVIs, and somewhere else in the network, behind some other switches, for example, we have the DHCP server. So what we need here is when the client sends the broadcast, when it sends the discover message, what we need this switch, this gateway here to do is take this broadcast message and send it as the unicast message towards the DHCP server so that the DHCP server can assign a proper IP address to our client. Now, the configuration of the DHCP relay here, and this device is now called the DHCP relay, is relatively simple. All we have to do in this case is configure the IP helper address on the interface and specify what is the IP address of our server. But this is not very simple operation that actually happens on this relay. The reason why it's not simple is that when we had our clients directly connected to the DHCP server, so as we had in our situation here, so we had the client, and let's say that we have a server here, that our iOS is not acting as the server. When the request came in from the client, it came in on a particular interface here, and based on which logical interface we received it on the server, which subnet we received it on, that told the server which pool to use. Now, in this case here, where we have a centralized DHCP server, all requests from all these 3 VLANs, so this is another VLAN, again unicast, and this is the 3rd VLAN here, again unicast. all these three requests are going to be arriving on the same interface here, or they could be arriving on the same interface. So the server here doesn't really have enough information to determine that this is one pool, that this is the second pool, and that this here is the third pool. This is where the relay comes into play. When the relay receives this original packet, and before it actually sends it out, it is going to insert in this packet here information about what is the relay's IP address. Now, this information here is something that is called GI address. Now, this address here simply tells our centralized DHCP server from which subnet or from which pool it should assign the IP address to the client. But as I said, the configuration of the actual relay is relatively simple. It's simply IP helper address and the IP address that we need to send our traffic to.